Yep, let me start joining the rest of the speakers and thanking the organizers, Matt, Adam, Christian, Laura, for this wonderful program. So yes, I will basically stop more or less at the point where Gemma finished, and my aim is to illustrate different quantum informational notions through the lens of non-local games. So the plan will be, roughly speaking, the following. So the first lecture, is that seen, or I need to write larger scene? Yeah, okay, good, thanks. The first lecture will be just, I will exemplify entanglement and self-testing through the CH-SH game. That will be dedicated to CH-SH game. And here we will see Bell's theorem, which is kind of an evergreen, and self-testing, which is kind of also a fairly old notion in quantum information theory, but kind of with recently revigorated interest in it. So the second lecture will be kind of moving from this particular case, let's say, really, this will be like a case study. We will move to more general non-local games, and I will talk about strategy representations and the NPA hierarchy. I will explain later how this, what the aim of the NPA hierarchy is.
Will you tell us today what NPA stands for?
Yes, this is Navasquez, Pironi, and Athin. These are the authors. CH-SH also stands for the authors, or the authors, the four authors that initiated the study of this game. So, lecture 3 will be dedicated to some examples arising from graphs, classical graphs. Lecture 4, I will motivate quantum graphs, starting from classical graphs, but through the lens of zero-error quantum information theory. So this will lead to quantum graphs. And the tutorial, this will be connections to matrix quantum groups, compact quantum groups, and teleportation the teleportation protocol that was described by Gemma. We will see that, in fact, the homomorphism game between graphs leads to connection to both of those things. So the idea is, I will try to give, like, I'm following this excellent example of Sergey, and it's difficult to live up to the start immediately after his lecture, right? To live up to this kind of to this promise that through his lecturing. So I will try to be to give the ideas behind the proofs and what's happening really. So yeah, I mean, any questions, please let me know. So the tutorial, what I want to say, the tutorial will not be something that is kind of special in that sense that I will give some tasks or anything like that. So it will be kind of more or less in the same style, which will be a little bit more encompassing than everything else. We'll make more connections, the last bit. But let's try to keep everything as a tutorial, maybe, yeah, in a sense. Right, okay, so what are non-local games? what's the non-local game? So a non-local game is a collaborative game. So it's a cooperative game. It's played by two players against a third party. So that's important always to keep in mind that there are these two players, Alice and Bob, and there is a third party verifier. And the verifier tries to test the joint knowledge of Alice and Bob, certain kind of pre-specified joint knowledge, very generally speaking. So mathematically, this is formalized by the verifier giving pairs of questions to Alice and Bob, they replying with certain answers, pairs of answers, and then the verifier checks whether the whole quadruple satisfies certain rules. So let's be even more kind of rigorous here. Verifier sends question X to A, to Alice, receives answer A from Alice. Similarly, they send question Y to Bob, they receive answer B from Bob. And then having this quadruple here, X, Y, A, B, so all these are finite. There are finitely many choices for the questions and for the answers. So X, Y, and B, they belong to certain finite sets. So X, Y, A, and B, they are finite sets. They will be fixed throughout the lectures. I will not change those. This notation, I mean. And then what are the rules? So the rules are described by a certain 0, 1 function, right, on the quadruple. So you will need to know, given a certain quadruple, whether the players win or lose. If the value of this 4-variable function is 1, the players have won against the verifier. If it's 0, they have lost the round of the game. This is for 1 round. If the game is playing 1 round, fair enough, this is what it is. Now, if it's played many rounds, what matters is how the verifier chooses the pairs of questions that he sends to the players. And this is done according to a certain probability distribution on the questions. So pi is a probability distribution probability measure, if you wish, on the pairs of questions. Right, very well. So fine. So this is what a game is. This is how it is played. And now, important assumption there, obviously, to make the things non-trivial, that Alice and Bob are not allowed to communicate. There is no communication between them once the game has started. Otherwise, obviously, they can send what they have received, Alice to Bob, and Bob will have all information.
Lambda is known to everybody.
Sorry?
Lambda, what is lambda?
Exactly. Lambda is the rule function. It's known to everybody, all 3 parties in the game. Yes. Lambda is known to everybody. Yes. Right. All right. Fine. So then they are not allowed to communicate. They can agree on some kind of way to play against the verifier before the game starts only. Right. After the game starts, they do not have channels of communication. Right. Very well. So then, what is kind of the simplest possible way, probably, to play this classically? This means that if Alice receives a question X, she spits out an answer f of x depending on x, determined entirely from x. So this is a certain map from x to a, questions to answers for Alice. And similarly for Bob, given y, he will produce g of y. So this is a certain function from y to b, with finite sets. So that's a possible strategy, right? That's kind of the easiest kind of strategy that one can imagine that the players will try to have, right? Mathematically, right? Formalized. The thing is that when will such a strategy be a perfect, let's say perfect means winning strategy for every round of the game, independently on the questions. So this would mean something like that your lambda has to satisfy, or the places where they win have to satisfy the condition that every time you have x and y questions for all possible questions, if you play with your strategy, f and g, Alice and Bob, that has to be 1, right, for all choices of questions, x and y.
Excuse me?
Yes?
when you say that Alice and Bob cannot communicate, it means that Bob does not know F and Alice does not know G.
Completely correct.
No,
Yeah.
no.
Yeah.
No. They can know F and G.
F and G, no, I didn't understand. I thought you were saying about X and Y. No, F and G is their strategy. It's a joint strategy. They are free to share this. This is not the problem. The problem is that Alice doesn't know Y, and Bob doesn't know X. So each of the players do not know what was the question of the other player.
But they can know the strategies of each other.
Sure. They can agree on F and G, what they believe is the best choice of F and G before the game starts, yes. Alice will be smarter than Bob, let's say, and she will say, no, what, you should use this strategy instead of this that you have in mind, right? So, fine, but they can agree on the strategy before the game starts. Yeah. I will formalize the non-communication kind of, yeah, this is not rigorously defined yet. I will define it in a short while rigorously. What is non-communication between them? Right, very well. So it's clear that this doesn't always happen. You do not need to have such functions F and G, right? Depending on your lambda, yeah. So, however, in practice, what is happening? The game is played many rounds, and if you are external observer of the game, what you see really is the questions and the answers alone, right? This is what you observe. So the referee gives, the verifier gives certain pair of questions. According to this pair of questions, the player spit out certain answers. So what you are really observing is just a conditional probability, family of conditional probability measures, probability distribution. So this will be the likelihood probability of answer A, comma B given question pair X, comma Y. Right, the game is playing like many times, and then you have some observation, statistical kind of observation of these values. So what an external observer will kind of, the view that they will shape up is just kind of some probabilistic kind of behavior, right? All right, so this is so-called probabilistic strategy. So this is a classical deterministic strategy, let's say, right? When you have this specific kind of deterministic way for Alice and Bob to reply. Of course, it will lead to certain probabilistic strategy. There's a 0, 1 valued, right? In that case. However, for example, they can just take, they can have several of those functions, pairs of functions. Fi, comma gi for finitely many of those, and every time they choose according to a certain probability distribution, or if you wish, two of them. They toss a coin every time, and they either use one or the other, let's say, right? Let's say. So you may have kind of combinations, convex combinations of such strategies, deterministic strategies, and this will lead you to so convex hull of deterministic strategies. This is what we call the local class of correlations or strategies. So when I say strategy or correlation, it will be the same thing for me for these talks. Yes?
So when you say someone tosses a coin, who exactly is tossing the coin?
Yeah, that is okay. I mean,
like an oracle or something like this, like some sort of resource.
Yeah, God, let's say, yeah, and communicates down, let's say. Yeah, but it's just you have some kind of mixture, kind of probabilistic mixture of such things, right?
But there are certain tricks you can do so that actually Alice and Bob can sample from a joint distribution without having to have any communication.
Say it again.
There are certain tricks you can do so that Alice and Bob can sample from a joint distribution.
Right. Exactly. One can have kind of a they can sample simultaneously with from certain probability distribution. They have the same I every time, and they choose Fi, Gi. Both of them use Fi and Gi for the fixed I every time. They may have shared randomness. Right, so you take the convex combination of all those, you arrive at this class C log. Another way to describe this class is the following. It is also the convex combination of the strategies, correlations that are given in the following way. I have something for Alice. P sub A. A is not a good thing. P1, yeah? P1 of A given X times P2 of B given Y. And here P1 and P2 are conditional probability distributions. So the difference is that there's just one variable once, right? One partite, each one of them. Yeah. So P1 is from X to A, if you wish, and P2 is from Y to B only. Right, so you can take these are well-defined bunches of numbers. If you wish, they are kind of numbers that depend on these four things, for variables, X, Y, A, and B. Right, so you vary your P1 and P2, you take a convex combination, you read them as vectors if you wish, right? You read the jumps as vectors in R plus, non-negative parts of R4 here. So this will be R4 plus, right? And here you need to have also XY, AB as well incorporated. So they're large vectors, right? So let me get it correct. These are vectors of that on that set. Yeah, these are vectors on that set. X cross Y cross A cross B, right? Yeah, non-negative entries. Vectors have non-negative entries. Take the convex combination of those. You arrive at a class of correlations, local correlations C log. All right. So these are the same, as I said, as the convex half of the deterministic ones. Fine. So then, what are there any other classes at all? So I mentioned in the beginning they are not allowed to communicate. So the most general class that you can define is the no signaling class. So this is class of correlations, which express exactly and nothing more stringent than not communicating. So this is the condition here. So P, and this is just a bunch of probability distributions of this sort, right? So this is index X, Y, A, B. This is called no signaling. If I can define, I can well define the marginal probability distributions, conditional probability distributions. So in other words, if I want to see what is the probability of A being produced given question X, answer A being produced given the question X, this should be well defined. What does that mean? Well, what is the way to define a marginal probability distribution, right? You need to slice. So let me try to do that. I need to kind of slice along the B variable here. So I need to add along B these numbers. I will get something. The trouble here is, in principle, it will depend on Y, right? This whole thing, in principle, depends on Y as well. And no signaling would mean that this will not depend on Y. So this exists independently of the variable Y, independently on the question to Bob, and similarly on the other side. So this is well defined. And similarly for B given Y, which will be the sum over A now. So this is well defined for every. This is the same value for any X, yeah? Independently of what you choose for X there. Right, so this is the whole no signaling class of correlations. Why kind of it expresses no signaling, lack of communication between Alice and Bob? Well, P of A given X, kind of if this probability is well defined, this means that Alice's behavior is kind of not influenced but by what Bob does. Independently of what Y is, what the question to Bob is here, Alice's behavior is kind of not influenced. There is no way for them to. If it were not well defined, this would mean that Bob would have a certain way to communicate to Alice what he is getting as a question. Right, so this is the mathematical formulation of the fact that the players are not allowed to communicate during the game. All right. Now, these are all no-signaling, so let me call C and S the class of all no-signaling correlations. Fine, so then let's see the example of the CHSH game, right? So what's happening there for these classes? I mean, at first sight, it's not entirely probably obvious immediately that these are different even, right? Not completely automatic. So the CHSH game, in this game, all the question and the answer sets are two element set, let's say Z2, 0, 1. I will take the probability distribution to be uniform here, so phi for any question pair will be 1/4. And what are the rules, right? So the rules are the following. Lambda of xy AB is 1 precisely when xy is equal to a plus b. And I multiply here in this field Z2 and add in this field. Right, so for this, this is kind of one of the basic kind of examples of a no-local game, and many kind of the features that one afterwards wants to generalize to study in other games, they're already present in this very small example. So the first thing is, so Sergei defined the tensor class of strategies and so on, and let's see what's happening with those here for this game. Well, first of all, let's see whether this game has a perfect deterministic strategy, so a local strategy, right? Whether it has a perfect local strategy is the same by convexity to have a perfect deterministic strategy, and you just look at it a little bit, and then you see that you cannot do that. There is no perfect deterministic strategy that satisfies these constraints. So the best that you can do is for any choice of strategy, you can satisfy the verifier, the rules of the game, 3 out of the 4 times you're being asked. So here there are 4 possible question pairs. 3 out of these 4 is the best that you can do. When you do not have a perfect strategy, a winning strategy, something that satisfies this relation, in that case, what it's kind of natural to do is how well you can do. What is the optimal winning probability of the game? Before that, let me state the definition of perfect strategy for general strategies. All right, this was for deterministic. Here just let me insert this definition. A strategy P, no signaling. So that's always no signaling strategy is perfect if, by definition, every time when some quadruple is disallowed by the rule function, then the de facto likelihood that this quadruple is produced in a round of the game is 0. It vanishes. Then we are talking about a perfect strategy. So in this case, there is no perfect local strategy, right, from the class C loc. And in that case, one would try to understand what is the optimal winning probability for the game. And this is the local value of a game. First of all, you fix a strategy for the players. If you are given a certain game, so it depends on lambda, it depends on pi, and it will depend on my probability distribution, this strategy. So this is just I need to sample a pair of questions. According to this pair of questions, I need to apply my strategy. And then I need to see whether it's verified or not, it's satisfied or not, whether it satisfies or not the rules. And the sum is over all x, y, a, and b. So this is the kind of the one-shot value of the game, right? Depending on on this strategy P. Now, if the players have a certain resource they're sharing, for example, all local correlations, then in that case you're trying to see what is the maximum of this, supremum or maximum of this of these values. So the local strategy of a certain game will be just the supremum over all P that belong to my local resource, C log, of all those values, lambda pi P. And you can see that for the CHSH game, as I say, so the value for the CHSH of local type will be 3/4. However, given kind of the axioms of quantum mechanics, as Gemma was, yes?
So one question. So log, what does log refer to? Is it the same log as above? So you're only taking.
Yeah, it refers to this C sub log thing.
So you're only taking a supremum over local strategies, right?
Correct.
The first one should be just omega lambda.
Sorry, say it again.
So the first one should be just omega lambda pi p. There's no log.
Yeah, here you do not need to put a log here. That's that's completely correct. Here I want to put the log because it designates the supremum over the local strategy. That's completely correct. Yeah. So yeah, the value here is that's completely right. Let me erase that. Yeah. So this is defined only for P. P is some kind of strategy, whatever it wants to be. Right? Doesn't matter. You can define this kind of number, which is a likelihood to win with this strategy. Then having a certain resource, which is a collection of strategies, you can define such a supremum, how well you can do with respect to this resource. Here, so omega log is when you play with the local ones. Yeah. Thanks very much. Yeah.
So the strategies are given by these P's, and we are finding supremum over all the strategies.
Right, so given a single strategy, you have a certain likelihood of winning, which is this one. And now you have a whole pool of strategies that the players share between them. And they want to select the best course of action, right? So the best course of action will be given at the strategy that attains such a supremum, right? This log, as I say, stands because I'm using local strategies here. Right, for CHSH, as I say, it's 3/4. Now the next kind of level of power of strategies is when they arise from measurements on a certain entangled state. So from the tensor model of finite dimensional, if you wish, model of forming joint systems. This was explained by Gemma, how you form a joint system. You have two finite dimensional Hilbert spaces representing the two systems. You take the tensor product, this is your joint system, and then you may have certain entangled states on the joint system, plus entanglement. You arrive at a class of strategies that is generally larger, as you will see, than the local strategies. So how are they defined? They're defined as follows. This again came about in Sergei's talk. You fix certain POVMs, x comma a. So this is a POVM along a. These are the outputs, the possible outputs. So you think of that as a kind of quantum function, if you wish. Here you have a deterministic function. Given x, you have f of x, which was a, element of a. Here you have these projections. X is fixed. You have these possibilities for an output of x, the a's. This, yeah, please. POVMs for the time being, yes. So this is just, they're not necessarily projections yet.
Positive.
Right, so this is a positive, okay, let me finish that for every x. For every x you have a different one, and this means simply that these are positive operators on a finite dimensional Hilbert space that add up to the identity operator along A for every x. Right, you similarly, so this is acting on finite dimensional Hilbert space. Similarly, symmetrically, you have something for Bob. These are again POVMs acting on some finite dimensional Hilbert space HB. And finally, you have a certain state. Let's view it as a vector. This was also kind of explained in.
Could you
yes.
say again where they come from? This EXA, what they would be?
So they are certain positive operators acting on some finite dimensional Hilbert space H sub A.
And where do they come from? What's the motivation?
Right. So I will write down the strategy and it will become clear. Yeah. Right. So I'm defining. So what I'm heading to now, I want to define a different class of strategies that use quantum entanglement. This is the aim. So having a vector C in the tensor product of these two Hilbert spaces of unit norm, I can form the following P then. P of AB given xy will be the following. So I take the tensor product of these two, I apply this to C. So as opposed to Gemma, I will be using just not the bracket notation, just the usual kind of inner product, linear on the first variable. Right, so basically, so I mean, back to Robin's question. So the physical motivation here is upon question X to Alice, she applies the measurement that corresponds to this variable X, little x, which is this one over here, to her part of the state of the system. Similarly, Bob is given a certain question Y. He chooses this particular, according to the question, he chooses the particular P of M measurement, applying to the part of the state, his part of the state. And then probability then that AB is given, provided XY are the input pair, is obtained in that way. So it is clear that this is no signaling, right? Because these were P of M's, and I will. This depends. This P, of course, it depends on all this data. So let me give a name for this. So
Can I ask
yes,
just make a link with what Gemma was talking about?
yes, please.
So we might be tempted to think about more general states than just vector states, but purification shows that
Very good
it doesn't
point.
matter.
Very good point. Exactly. Very good point. Indeed. Yeah. I mean, in general, here we can apply not necessarily a vector state to this tensor product operator, right? We will see that it is the same thing, either by purification or just it is essentially purification, right? I mean, you can. Yes. I mean. Okay, I will give the, okay, let me give, so C sub Q is the set of all strategies of this type, which are called quantum strategies. It's a convex set, right? So this is one of the, it's equivalent to what Matt is saying, right? Being a convex set is the same as being able to take here vectors that are states that are not necessarily pure states. All right, so this is, let me put it here. All these are kind of, things that can be kind of easily verified, so I don't stop really to talk about them. Right, so it depends on all these data. So let me call M this bunch of data. So I have all those things here, right? I have the F's, the measurements of Bob, and I have the vector. So this is a tuple consisting of the spaces, the Hilbert spaces, the corresponding measurements, all families, and the unit vector C. This we call a model for P. And let me say that P is P sub M, right? It depends on the model. So this is a quantum model. Let's call it a quantum model, all right? And we have a class of all correlations arising from quantum models is the quantum strategies. Set of quantum strategies. This I didn't use, all right? So
You can use the top if you wish.
which one?
You can use the top.
Here.
Above the line.
But not that one. Yeah.
No.
Okay. Sure. Is that okay?
Yeah.
All right. So now, what is the corresponding value for the CHSH game if you play with the quantum resource? If the players share the quantum resource, all quantum strategies, is there, for example, a perfect strategy? Right. So no, there isn't. In fact, so given any resource, So let me define first the general value. So given any resource R of strategies, one can define a corresponding value of the game, of any game that you have in mind, as the supremum of the corresponding localized values, strategies from strategies coming, over strategies coming from the resource. And when I write subscript q, this will be just the corresponding thing for C sub q, the quantum class. All right, so for the CHS game, what is the statement? So this is kind of a proposition here. The quantum value of the CHS game is a half plus 1 divided by 2 times square root of 2. And if you have kind of more aesthetical inclinations, I would write it as cosine pi over 8 squared. I don't know which one is more beautiful, right? I don't know. Yeah. So these are the same. All right, so why is that true? So I need to show two things here. First, that there is a way to achieve this using a quantum strategy, and no other quantum strategy will give me a higher value. Right, so let's kind of sketch of a proof, not complete proof, but sketch. Right. So it will go like that. So what is the strategy that reaches this, at least this value? So this will be the following model. I will have, let me give a certain notation here. As a vector in C2. I will need to define for every x, which is either 0 or 1, I need to define two projections. I will define, it will be projections actually, not only positive operators. So 0, 0. For Alice, it will be the rank 1 projection corresponding to this vector. So this is just 1, 0 vector, the standard basis vector. And the other one will be, of course, the orthogonal complement, because they need to add up to 1. Then for 1, 0, it will be, I need to work with pi over 4 here. And then for Bob, on the Bob side, I will have pi over 8 angle and minus pi over 8. What is the vector? The vector will be the maximally entangled vector. So that's okay here up to here, right? Okay, so C will be the maximally entangled vector, which is the sum of the bases normalized. So then you sit down, you roll up your sleeves, and you kind of make the computation, and you see that it is exactly this value here. This strategy gives exactly this value. It's just a computation. Why are these projections? So this will become clear really in a short while. Why this is a good choice? Why this is the choice that works? It will very shortly kind of becoming clear why. Right. So for this one, I have that the model, the corresponding model, is the corresponding value then of CHSH will be exactly the value that I have here. So it's more interesting, maybe, why is the opposite, the converse true? In other words, why I cannot do better than this? And here is the reason. So first, the Q class can be equivalently defined using projection valued measures. That is, this means that the corresponding EXA are projections. Right? And they are, of course, self-adjoining still. And similarly for F. So if you just restrict to projection valued measures, the class that you obtain is the same. So this is what Verne likes to call the disambiguation. I think for correlations, you can define them equivalent using projections. Why is this true? So I will give a kind of a general argument for that that will follow in all cases, not only for the Q class. One can do it for the Q class separately using much simpler arguments. For the QC class that Sergei defined, one cannot get away so easily. One needs a little bit more there. So I will do that. So this note I will do a little bit later. So for the time being, I can just assume that I have projections in my model. So in that case, if these are projections, remember I have only two here, the status over 0, 1. I will form the corresponding symmetries arising from these projections. So let's see now. This one, for example. Right, so for every given x, 0, 1, if I form the difference of these two, this will be a certain unitary, self-adjoint unitary. And vice versa, from a given self-adjoint unitary, I can recover the two spectral projections corresponding to 1 and to -1. So this is just an operation that can go both ways. Similarly, on the other side, on both sides. All right. So then I will define then in that case what's called the model operator. So I'm starting with a model, right? So maybe I should be a little bit more precise here. Start with a certain model. Right, so I have all this data here, right? HB, and let me write then AX here and BY now because they recover the projections uniquely, and a certain vector C. So starting with a model like that, I can define the model operator. Beta, which is just, I will do that's the model operator of the operator of the model. And now one verifies the following. So one sits down again and checks that the value is related like that. So this is what I will use. So let me get this right. If I'm playing with a strategy corresponding to this model, this depends on the model, of course. This will be the same thing as 1/8 of the model operator applied to my vector C, paired with C, plus another half. Okay, and then the crucial thing here is why do I have the inequality? Remember, I want to show that this omega value is smaller than the value that I have here, 1/2 plus 1 divided by 2 times square root of 2. So it boils down to some inequality about this term of this kind of sum. I need to show, in other words, that this term is not more than so need to show this inequality. And why is this true? Well, this is true because if you form 2 times square root of 2 minus your model operator, you get a positive operator, independently of the vector. So this I need only on the vector, but actually it's true globally, generally. So this is the, this has the factorization. Let's see whether I will remember it correctly. So I think we need to do A0 plus A1 divided by square root of 2 times the identity minus the identity times B0. I need to square that, and you need to have similar things here. times tensor with b1 squared again. And I believe you need to probably take a half here. I'm not sure I need to take a look at my notes for the correct term. Yeah, it's a half. So that's correct with half. So that's a positive thing. So therefore, you have this inequality, and we are done. So this is kind of the reason why you have this computation of the result for the Q value. So shall we make? That's the end of it, right? For the time being, yeah, isn't it? Yeah. Okay.
Yeah.
Okay. Sorry about that. I thought I have another continuation, but yeah. Okay.
No, we
Okay.
started.
All right.
Anyone got any quick observation or question?
Maybe one.
Yes.
One.
So the quantum case is supposed to contain the classical case.
Correct.
In classical case, what this POVM scale goes?
So they will be just scalar valued, right? So if you fix your x, these will be just scalar valued things already. And remember that x is fixed, and you need to have a POVM for fixed x. Well, this is a POVM, one-dimensional POVM acting on the scalars. This is for the elementary ones, and then it's closed under. This I didn't mention. I mean, I mentioned that they didn't prove convex combinations like those. You will have commuting operators. If you have a certain mixture, probabilistic mixture, you will have a corresponding kind of diagonal matrix here, right? With the entries coming from these POVMs, the one-dimensional POVMs.
Thank you. Maybe we can start the next session with your question. So let's thank everyone for